Start with the basics. The circuit breaker pattern is a powerful design strategy used in cloud applications to handle faults when connecting to remote services or resources. Imagine you're calling a service that's down or slow. Without a circuit breaker, your app might keep trying and waste resources. The circuit breaker steps in to temporarily block access to the faulty service, preventing repeated failed attempts. This helps your application recover more effectively and keeps the system stable, especially in distributed environments where failures can cascade and impact unrelated parts of your system. Distributed systems calls to remote services can fail for many reasons. Maybe a server is overloaded, the network is slow, or a resource is temporarily unavailable. These are called transient faults and they usually fix themselves. But sometimes failures last longer, like a complete service outage. If your app keeps retrying in these situations, it can block resources and even cause more failures. The circuit breaker pattern helps your app recognize when an operation is unlikely to succeed and stops it from trying again until there's a good chance of recovery. Circuit breaker pattern acts as a proxy between your application and the remote service. It monitors the number of recent failures and decides whether to let requests through or block them. If failures exceed a certain threshold, the circuit breaker trips and blocks further attempts for a set period. This gives the system time to recover and avoids wasting resources on operations that are likely to fail. Once the timeout expires, the circuit breaker allows a few trial requests to check if the service has recovered. Circuit breaker has three main states: closed, open, and half open. In the closed state, everything works as normal, requests go through and failures are counted. If failures hit a threshold, the breaker moves to the open state where all requests fail immediately. After a timeout, it enters the half-open state, allowing a limited number of requests to test if the service is back. If those succeed, the breaker closes again. If not, it goes back to open. This cycle helps balance recovery with protection. The closed state, the circuit breaker lets all requests pass through to the service. It keeps track of how many requests fail within a certain time window. If the number of failures stays below the threshold, everything continues as normal. But if too many failures happen in a short period, the breaker trips to the open state. This approach helps avoid overreacting to occasional minor glitches and only trips when there's a real problem. When the circuit breaker is in the open state, it immediately fails all requests to the service. This prevents your application from wasting resources on operations that are likely to fail. The open state lasts for a set timeout period, giving the remote service time to recover. During this period, your app can return default or cached responses to users, maintaining a better user experience while protecting the system from overload. After the timeout, the circuit breaker enters the half-open state. Here, it allows a small number of trial requests to check if the service has recovered. If these requests succeed, the breaker resets to closed and normal operations resume. If any fail, it goes back to open and starts the timeout again. This cautious approach prevents a recovering service from being overwhelmed by a sudden flood of requests. It's important to understand how the circuit breaker pattern differs from the retry pattern. The retry pattern is used when you expect a failure to be temporary and want to try again, hoping for success. The circuit breaker pattern, on the other hand, stops trying when it's clear that the operation is likely to fail. In fact, you can combine both. Use retry within a circuit breaker, but make sure the retry logic respects the circuit breaker's state and doesn't keep retrying if the breaker is open. Additional circuit breakers use fixed thresholds for failures and timeouts, but this can be too rigid. Modern systems can use AI and machine learning to adapt these thresholds in real time based on traffic patterns and historical failure rates. This makes the circuit breaker more resilient and efficient, adjusting automatically to changing conditions and helping your application stay robust under varying loads. In implementing a circuit breaker, consider exception handling, monitoring, and recoverability. Your app should handle exceptions gracefully, perhaps by degrading functionality or providing alternative data. Monitoring is crucial. Use distributed tracing and logging to keep an eye on both failed and successful requests. Also, configure the circuit breaker to match the recovery pattern of your operation, so it doesn't stay open too long or switch states too quickly. There are several advanced considerations for circuit breakers. For example, you might want to allow manual overrides, so administrators can reset the breaker if needed. In large distributed systems, be careful with concurrency. Don't let the circuit breaker block too many requests or add overhead. Also, differentiate resources. Don't use a single breaker for multiple independent resources, as this can block healthy parts of your system unnecessarily. Circuit breaker pattern is ideal when you want to prevent cascading failures, protect against slow dependencies, or manage intermittent connectivity issues in distributed environments. It's especially useful for maintaining service-level objectives and avoiding performance degradation during high-latency events. However, it's not suitable for managing access to local resources or as a replacement for business logic exception handling. Let's look at a real-world example using Azure Cosmos DB. Suppose your app uses the free tier, which has a quota. During peak demand, you might hit this quota and get 429 errors. A circuit breaker detects these errors and trips to the open state, returning cached or default responses to users. Azure Monitor logs the events and alerts the operations team. Once the load drops or capacity is increased, the breaker resets and normal service resumes. This approach keeps your app stable and cost-effective. This Azure example, the main components are Azure App Service, Azure Cosmos DB, and Azure Monitor. The App Service hosts your web app and enforces circuit breaker policies. Cosmos DB stores your data and benefits from traffic limiting during overloads. Azure Monitor aggregates logs and metrics, triggering alerts when thresholds are breached. This setup ensures your app remains responsive and stable, even during unexpected demand spikes. Wrap up: the circuit breaker pattern is a must-have for building resilient, stable cloud applications. It prevents repeated failures, protects your resources, and helps your app recover gracefully from outages. Always monitor your system, tune your breaker settings, and combine with other patterns like Retry for best results. By understanding and applying this pattern, you'll be ready to handle faults and keep your services running smoothly, no matter what challenges arise.